Hello everyone. My name is Ashish Kade and my group members are Akash, Sagar and Prathamesh. And our faculty's name is Professor Shilpa Rudravar. Today we are presenting on our review paper, Technology Advancement and Challenges in Mosfet Scaling. Uh, we'll start with the introduction. We know MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. Is a type of voltage controlled field effect transistor. We know MOSFET is an essential building block of an NIC. Because of its advantages like low power consumption, low cost of manufacturing, then fast operation speed, etc. It is a very dominant device in digital and analog as compared to any other semiconductor devices. In this presentation, we have conducted the systematic literature review on the MOSFET scaling and challenges faced during scaling on 5 research papers from the IEEE since 2001 to 2009. While carrying out the review, we come across some of the scaling technologies. These are stage engineering, shallow junction formation, and high K metal. We will talk about these technologies in further slides. So let's start with the stage engineering. First technology, that is the new technology used for MOSFET scaling, is the stage engineering. But first of all, why this technique is introduced and why it is required. The reason is the shrinking of device size is essential but not sufficient, because the simple scaling is reaching the limit in terms of scaling and CMOS performance improvement. So this stress engineering technique is used to boost the carrier mobility and the MOSFET performance. In this, there are two kinds of PSG, that is polysilicon gate, were applied to N MOSFET fabrication processes. The one is the after offset spacer formation, that is OS PGS, and the other is after source drain ion implementation. By optimizing this PGS process, 23% improvement of N MOSFET's ion of performance was successfully obtained. Now the next technology is shallow junction formation, which is explained by my colleague Prathamesh.
So first of all, what is shallow junction? Shallow junction term refers to the depth of the source and drain in advanced CMOS and MOSFETs. Scaling requires continued reduction of this junction depth, and it can be as shallow as 10 nanometer. This shallow junction formation includes two processes: dopant implantation followed by annealing. Because of high dopant activation, high profile abruptness, and low contact resistance between doped Si and NSI, demand for this ultra shallow junction formation technique is increasing. For the activation of ion implanted dopants, various annealing methods have been proposed. Among them, FLA, which is flash lamp annealing, is highly considered because of its diffusionless and high dopant activation feature. Application of this FLA to high K metal gate device degrades carrier mobility and negative bias temperature instability. This is probably because of increasing electron trapping site in a high K during FLA treatment. So in order to recover from such degradation, additional thermal annealing, that is recovery annealing, is necessary. But this degrades shallow junction characteristics. So the new flash lamp annealing technique, that is flexible shaped pulse flash lamp annealing, is proposed. This FSP FLA has a feature with new pulse shape in which high power short pulse and low power long pulse are combined. By using this FSP FLA, electron mobility and NBTI degradation is improved to the level of conventional FLA. And next technique is next slide, high K metal stack. So this high K metal gate stack technique is required for scaled MOSFET in order to achieve the low gate leakage current and high current drivability. One of its major problem is the threshold One of its major problem is threshold voltage control. So dual metal gate, before this technique, there was a dual metal gate R proposed, but they still suffer from insufficient threshold voltage control. So here the single metal and dual high K gate stack is proposed in this technique. In this technique, SMDH CMOSFET was fabricated with Al2O3 containing high K for P MOSFET and MgO containing high K for N MOSFET. Common stack formation with TIN metal gate and HFSiO were fabricated in a standard gate. For the P MOSFET, it was clarified that the Al2O3 insertion position was successful in controlling the threshold voltage. So next, the limits will be explained by Akash.
So, for limiting the scaling of MOSFET, there were many factors which were affecting the scaling of the MOSFET. The major two were the leakage current and the tunneling current. So, the leakage current problem arises because of different applications, because each application requires a different design, and due to which power consumption is different, and due to high power consumption, leakage current problem arises, which was the major factor for limiting the scaling of MOSFET. Uh, the second one is the functionality of the circuit, because as the application is different, functionality will definitely be different, and due to which power consumptions will be different, and which affect the leakage current problem. So there were many constraints which work out for these different applications, like we can use dynamic random access memory, static random access memory, low power portable devices we can use, and moderate and high performance CMOS logics we can use. The another second major factor was the tunneling current limitation on scaling. As the tunnel length shrinks down, there was a serious problem of tunneling current, because uh, because through the gate oxide the tunneling current problem arises. So due to which the more power is drawn, and it affects the device performance. So looking into this problem, they have come to three solutions, that we should stop scaling the gate oxides, and we can scale the rest of the MOSFET. The second way was to change the device structure uh, to one in which the gate essential surrounds the channel. Means the gate essentials will be surrounding the channel, and the overall structure can be changed. And then third way was to they tried to change the gate insulator with another material. So these were the two major factors. One was the limiting current, and second was the tunneling current, which limits the scaling of MOSFET. Now I'll invite Sagar to conclude all these.
So, as my colleagues are told everything about the technologies and the scaling factors, so I will sum up all of these points in the conclusion. So, we have gone through the different MOSFET scaling technologies that are played a very much important role in the while scaling the MOSFET, such as multiple stress engineering, ultra shadow junction formation, and the last one, high K metal gate. We have also seen the various parameters that actually affect the MOSFET while scaling down. As we know that firstly there is a Moore's law which is talking about there is the MOSFET scaling in every 2.5 years. But now by considering all of these parameters and the factors, we have come up with the some of the limitations while the MOSFET scaling, that this much of the innovations is not happening now. So next slide. Yes. For this review paper, we have gone through these five research papers, and which are the IEEE journal papers, basically from the 2001 year up to the 2010 year. We have gone through the papers like downscaling limits of the SI MOSFET and their application dependencies. We have gone through the MOSFET scaling trends and the challenges through the end of the roadmap. We have also gone through the other research papers also that are MOSFET scaling to nanometer against that we have seen the nano devices like now. So, what is that purpose at the 2007 year where nano devices are getting formed? So we have gone through that research papers also for our review paper. And also there are the papers like scaling challenges of the MOSFET for 32 nanometer node and beyond. Also the scaling the bulk driven MOSFET. We have gone through all of these review research papers for our reference paper, review paper, sorry. So next slide. Uh, we have submitted our review paper for the publisher also at the research conference website, and we have got this paper code 72, and they have next slide. Also they have accepted our review paper for their conference which going to be held on the 14th and the 15th in this month of the November, uh, under the engineering technologies research papers, engineering and management. Uh, I would like to say while the concluding this whole of this our PPT that by reviewing this PPT you will get the overall whole idea about the how the MOSFETs are get formed and how the MOSFETs are getting scaled down to get our devices so much of the combat. So thank you very much.